This is part 2 of our quick introduction to Julia sets. The easiest kind of function is a constant function. In this animation, f of every point a plus bi is going to equal the constant 0.5 plus 2i. While you watch the animation, you should think about the question, what are the fixed points of this function? Again, the cursor represents the point a plus bi, and the arrow points to the image of that a plus bi. And as you can see, no matter what point we start with, the image is always the point 0.5 plus 2i. The second easiest function might be the complex function analogy to f of x equals x plus c. For example, let f of a plus bi, f of x, equal a plus bi, that's the original x, plus the constant 0.5 minus 0.5i. This function creates an exact duplicate of the points a plus bi, only moved over by half a unit and down by half a unit. The previous animation should remind you of vector addition. Note that iterations of this function are pretty tame. In the next animation, we show the first four members of the orbit of the input point a plus bi as this point is moved around the plane. How would you describe the long-term behavior of any of these orbits? Note there are four arrows on the way from a point a plus bi to its fourth iterate, representing the process of moving over by a half and down by a half 4 times in a row. Now let's see what our formula for computing x squared plus c becomes when x and c are complex numbers. First, it's tradition to let z replace x as the variable. So let z and c be complex numbers. We need symbols for their real and imaginary components. We could write let z equal a plus bi, but it will be much easier to keep track of computations in writing a program if we say let z equal, and then you see these two symbols here which stand for the real part of z and the imaginary part of z respectively. So if z is the complex number 0.2 plus 0.4i, we have re-z equals 0.2 and im-z equals 0.4. Similarly, we let the complex number c be represented by re-c plus im-ci. You should work out the following formula for yourself and verify that z squared becomes the complex number whose real part is the square of the real part of z minus the square of the imaginary part of z, and whose imaginary part is 2 times the real part of z times the imaginary part of z. This animation shows that 0 squared is 0, minus 1 squared is 1, and minus 2 squared is 4. Let's follow the image of a circle of radius less than 1. Note two things about the image circle. Number 1, it wraps around twice. Number 2, its diameter is smaller than the original circle. Here's a trace of the squares of all the points on a circle of diameter bigger than 1. Again, there are two things to note. Number 1, the image circle wraps around twice, and number 2, its diameter is bigger than that of the original circle. Now let's have a look at the images of points on the unit circle. This image circle wraps around twice again, and it is the unit circle itself. So the unit circle is mapped to itself by the function z squared. This next animation suggests that the orbits of points outside the unit circle escape to infinity. This clip suggests that the orbits of points inside the unit circle converge to 0, and that 0 is an attracting fixed point for the function z squared. If the complex number a plus bi is on the unit circle, so is its square, and therefore the entire orbit lies on the unit circle. In this clip, the original point is barely moving, but its 10th iterate is zipping around, an indication of chaos, as points that are originally close together have orbits that spread far apart. On this frame, we show a point which has I in its orbit, and then I squared equals minus 1 in the orbit, and finally 1 is in the orbit. So the original point is an eventually fixed point. When we studied the function x squared with x real, your bifurcation diagram showed that x squared has one attracting fixed point and one repelling fixed point, and no points of any other periods. But its complex counterpart has points of every prime period, densely packed throughout the entire unit circle. These three short clips show one way we might graphically search for points in prime period 5, or prime period 3, or perhaps points in prime period 8. If f of z equals z squared, then, these animations suggest that 1, if the modulus of z is less than 1, then the orbit of z converges to 0. And 2, if the modulus of z is greater than 1, then the orbit of z escapes to infinity. And 3, the orbits of points on the unit circle may exhibit chaotic behavior.